Bon, je pense qu'on peut commencer. Donc, c'est un très grand plaisir aujourd'hui d'accueillir Giuseppe Carleo. Comme vous l'avez compris au cours des cours précédents, Giuseppe est un pionnier du domaine, en particulier grâce à son célèbre article de 2017 où il a introduit les réseaux de neurones pour paramétriser les fonctions d'onde. Donc, je vais vous dire quelques mots sur Giuseppe. Giuseppe fait l'université de Rome, puis il a fait sa thèse à la Sissa, à Trieste, avec Stefano Baroni, mais je pense aussi avec beaucoup de discussions avec Sandro Sorella, dont la disparition tragique nous a tous marqués il y a quelques mois. Ensuite, Giuseppe est venu en France, à l'Institut d'optique, je pense avec une bourse Marie Curie, si mes souvenirs sont bons. Et en ce qui me concerne, j'ai rencontré Giuseppe la première fois grâce à un événement extrêmement rare, un retard de bus en Suisse sur un quai de gare pour monter à l'ETH. Pour ceux qui connaissent, je pense que c'était Egbourg, un truc comme ça. Voilà, Milchbourg. Il y avait beaucoup de neige et les bus étaient en retard. Ça n'arrive pas souvent, mais ce genre d'événements vous permettent de rencontrer des gens exceptionnels. Donc c'est là où j'ai rencontré Giuseppe, je crois, pour la première fois, alors qu'il était venu à l'ETH dans le groupe de Mathias Troyer, et où il venait d'écrire cet article que j'ai déjà cité. Et grâce à cette rencontre, entre autres, Giuseppe est venu passer quelques années à New York, où il a été project leader dans le domaine du machine learning. Et puis ensuite, il a brisé mon cœur en quittant le CCQ et en venant s'installer à l'EPFL, où il a une chaire de, je pense, quantum computing ou computational quantum sciences. Voilà. Donc, il a évidemment une très grande activité dans ce domaine et on est très content de l'accueillir aujourd'hui pour nous parler de time-dependent neural quantum states.
Merci Antoine, merci à toutes et tous pour être venus. Je vais faire mon cours en anglais, donc welcome everybody and thank you Antoine for organizing this great series of lectures. So today my contribution will be about time-dependent neural quantum states. So I will tell you about ways of studying dynamics rather than ground state properties, as you might have seen, for example, in the last lecture, last week, especially from Antoine.
The one thing I didn't say is that I would encourage you to ask questions during the talk.
Yeah, you're very welcome to ask questions, and I will be happy to answer if I can. So as a small recap, essentially what you saw, again, mostly in the past lectures, were ground state, if you want, problems. So I will do part of my lectures on the blackboard. My handwriting is terrible, so if you can't read, please ask me. So for ground state problems,
Can you use white chalk?
Oh, this is just for the title. So for ground state problems, so what is the idea? As you know, so given a many body in general, the kind of Hamiltonians we're interested in are typically interacting problems of many body particles, H. So you would like to find some, so you would like to find its ground state ideally, psi 0. However, as we've seen, as you know very well by now, the problem is that typically the space in which this ground state wave function lives is too big, and it is more convenient if you want to, if we want to have a good approximation or a good handle on this problem, to rather approximate, if you want, this psi 0, this exact ground state wave function, by restricting our attention to a manifold of quantum states that I will call here psi theta, where theta now denotes a set of variational parameters that somehow allow you to span a limited but hopefully large enough region of states, quantum states that cover your Hilbert space of wave functions. So, and the main idea then is that if you want, we transform this complicated, if you want, eigenvalue problem into a minimization problem where we define a loss function in, I'm already using, if you want, machine learning jargon, which is pretty much given by the expected value of the Hamiltonian on your variational state psi of theta that here I'm assuming to be normalized. So the main, if you want, ingredient that we've been using then is that by virtue of the variational principle, we know now that this object is strictly larger or equal than the exact ground state energy. And again, if our variational state psi of theta is expressive enough, as we say, so if it covers, again, a large enough region of the space of wave functions we are interested in, we can hope that we will have a very good approximation for the ground state energy and also of all the other properties. So, and as have you seen, the idea was, for example, in the context of machine learning, is to represent, for example, I will not write it down again, but to represent these wave function amplitudes as artificial neural networks, for example, this RBM that we started using in the first paper in 2016. So far, so good. So we have a formulation, if you want, of this ground state problem as a minimization problem, right? So we have transformed the original eigenvalue problem into a minimization problem over the theta variables. And this is good. So because we have prepared, in a sense, our physical, if you want, problem into a form which is suitable for the machine learning framework, which is especially tailored and especially suitable for minimizing, if you want, a high-dimensional cost or loss function, as we say in jargon. Now, however, if you do a slight, if you want, a step back, and you go at the origin of this equation, so one of the reasons you want to study the ground state problem is because actually you are interested in solving the actual Schrödinger equation, right? So sometimes in the literature, we call this the time-independent Schrödinger equation, but the actual Schrödinger equation, as you know, or the one that I would call the actual Schrödinger equation is the time-dependent version of the Schrödinger equation. So I will use the notation that I have here. So I have my state, generic state phi of t, and this is given. So the time evolution of this state is given by h applied on my state, right? So here I'm assuming that h, the Hamiltonian, is time independent, but we can generalize this easily to the time-dependent case if necessary. So the reason why we want to study this is because these are stationary states of this, right? So if you want, we have to go back, or if we really want to solve the Schrödinger equation, we have to go back to the time-dependent problem and see if we can find a way to fit this problem in a way that is suitable for machine learning. So there is a novel by Philip Dick, famous sci-fi writer, where essentially in a slightly dystopian world, humans were at the task of cleaning up metals and feed them to highly sophisticated machines. So, and in a sense, that's our task here, where we are cleaning up the original problems in a way that is suitable for our favorite machines. It's a slightly, dystopian way of looking at the problem, but it is not far from the reality, especially if you look at how some of the ChatGPT applications work these days. Now, let's have a look how we can do this more specifically. So in a sense, we want to transform this problem, which is now, a time-dependent differential equation, an ordinary differential equation, into an optimization problem. So this is more general than the standard, more general than machine learning, but it's a topic which is not often treated in standard, I would say, quantum mechanics courses. So I will give you a short overview of how we do this. So the main idea that we will use here is that I will introduce time-dependent variational states. Okay? So this means that I will give some time dependency to my variational parameters. So instead of having some fixed variational parameters, here I'm assuming that my theta, so the variational parameters, can depend on time. Okay? So this then will identify, once I set up the time dependency for theta, if you want, how my variational state will evolve in time. So the main question then is, how do we find theta of t, right? So what does it mean to find an optimal, in a sense, theta of t that exactly or approximately reproduces a solution to this original problem? So the main idea is that we want to, of course, find this theta of t in a way that they satisfy as close as possible to this equality, right? So we want that they match as much as possible the exact time-evolved state. And geometrically, there is a nice way, if you want, of looking at this problem, which is quite informative. So if, for example, I assume that at time t, my state that lives now, just for simplicity, in a two-dimensional Hilbert space, right? So I'm, if you want, depicting my quantum state at time t in this way, okay? So I'm assuming that I'm starting with some exact, some initial state at time t, which is given by some variational state that I will call psi of theta, okay? So, and this is nothing but a vector in this case, a slightly simplified, only two-dimensional Hilbert space. It's the only one I can draw on the blackboard. So then what happens is that if I evolve this state in time, I know that after a short time step, delta t, its exact time evolution will be given by this vector, let's say, okay, that I will call phi, right, so sorry if this is not great, but so this will be phi of t plus delta t. So what is phi of t plus delta t? I'm assuming that I have a small time step. So this means that my phi of t plus delta t will be just if you want, the exact time evolved state. So psi of t minus I delta t, the Hamiltonian applied on the initial state that here I called psi of theta with some initial parameters that we don't care about too much now. Okay, so I just linearized, if you want, the Schrödinger's equation for a small time step. So again, this is unitary, so I expect that this to be just a rotation of my original vector in this Hilbert space. On the other hand, since I'm assuming that psi, so my variational state depends parametrically on my thetas, and I'm giving some time dependency to the variational parameters, I can also linearize my state, right? My variational state at time t plus delta t. However, the only dependency that I have in my variational state is given by the fact that my variational parameters have changed after a time step delta t, right? So this means that I can write this as, if you want, my state, my phi of theta at the initial time plus delta t, and then I have a sum for k that goes to 1 from the total number of variational parameters of the time derivatives theta dot of k, right, at time t times the derivative of my variational state. So I'm inconsistently using square and regular brackets, but I hope that you get the idea. So you see now that I have two vectors. So the red one is the exactly evolved state, and the yellow one is the approximate now evolved state. So I can, if you want to just denote it like this, and you can see that these two vectors. So in general, the yellow vector will depend on how much I will change, if you want, or will depend parametrically by the time derivatives of my variational parameters. So this means that I can make this yellow vector rotate, if you want, to some extent, in order to match the actual time evolution, which is the one given by the red curve. So this is the idea, yes?
Excuse me, is it a psi after the h on the first equation, or is it a phi?
Yes, sorry. So as I was mentioning, the initial state is the same for both cases. Yeah, this is psi. Sorry about that. Yeah, so this is psi of theta of t, right? So let's write like this. Okay. So the initial state is the same one. The only thing that I'm looking at is the generator, if you want, of the dynamics, and I'm matching the state after a certain time step. Okay? So what does it mean to match the states? Well, it means that I have to match these two vectors, the yellow and the red one. And one, if you want, way of doing this is to write the distance, if you want. In this case, I'm assuming that both vectors are still normalized. So I can define a suitably renormalized distance with the time step delta t square, which will be essentially just the L2. So if you want the distance between these two vectors in square norm. Okay? So this will be just, so if you want the first term that we have here, so it's k sum of theta over k of theta dot k of t. And then I have, let me also use already this notation where I insert, if you want, the derivative inside the ket for reasons that will be apparent in a moment. So this is, if you want, this first order correction that I'm putting in here, and I'm already absorbing the delta t here. And then I have the other vector. Then I have to take the difference, so I will have plus I, right, h psi squared. Okay, so that's why there is a square here. Okay? So this is, if you want, the rate of change in my L2 distance between my two quantum states. And I would like, ideally, to have that this distance is as small as possible. And as you can see, this distance, so this delta square, is only a function of my theta dot, so of my time derivatives. So I managed to rewrite the problem of approximating my state at the next real time in this step of Schrödinger's dynamics into the problem of minimizing this loss function, delta square over delta t square, that depends parametrically only on the derivatives of the theta k. Remember that theta here is fixed because these are the initial parameters for my initial state. Okay? But however, here we don't need complicated optimizers because this is a quadratic form. So actually we can very easily rewrite this as the sum over k and k prime. So I'm assuming that my parameters are real, and so are their derivatives in time, right? And then I have here. So since I'm taking the square of this term, so I will have the derivative of this, and then I will have theta k psi. Okay, so this is relatively simple. It's the square of this term. And then I will have plus I, and then I will have sum over k. So I will have all sorts of terms. And let me just write the most important ones, and which is this one, for example, psi h. And then I have the derivative with respect to theta k of psi. Then I have all the Hermitian conjugate, so the complex conjugate of this term. And then I will have another constant term that depends on, that I will not write down, that contains h squared, but that does not depend on theta dots. Okay, since I want to minimize now this distance, and I will want to take derivatives, I don't care about the other term. So after all this, if I now take the gradients of this with respect to theta dot, again, my only degree of freedom in this equation, I end up with the following equation. So sum over k prime of theta dot k prime at some time t, the real part of this object here that you might have already seen during this course that we call the quantum geometric tensor. So this is the k psi theta k prime psi. Okay, here there's a sum over k prime, and then I have on the other. So I'm not doing the full calculation, but it's very simple. You just have to take the gradients of this and set it to equal to 0 of the imaginary time of this other overlap, which is this object here. Okay. So what you see is that by minimizing this distance at each imaginary time, I found an equation of motion for my variational parameters. So I know what is the equation that my variational parameters derivatives have to satisfy in order to minimize this distance. So in a sense, and in this very specific sense, this is what we mean by optimality in describing the time evolution with a variational state. And you see that this equation takes the form, essentially, of a system of equations where I have introduced this object as kk prime, and this must be equal to some f of k. So if you want, this is a linear system to be solved for the unknowns theta kk prime given s and f. Now, what are s and f in the more general case in which these two states are not normalized? So I will just write down for you the final equation. So as I was mentioning now, I was assuming that psi and phi are normalized, which is not always the case, especially for variational states. But if you take into account also the normalization, so these now will contain, so these quantities will contain, if you want, other terms that come from the normalization. So you will have this overlap here, and also the, so here I'm taking the real part of these objects, okay? And then, sorry, and this is the imaginary part, okay, as in there. And then the other part that I'm missing, so if you want here, would be the, right, so this would be the expected value, so this term. Times psi. Okay, so I'm not deriving in detail why these terms arise, but they come essentially from the fact that your variational state is not normalized. You can derive them easily. And then the same for this f of k, where in addition to that term that you can already see written there, so the derivative of psi and then h psi, you also have another term which arises because of the normalization. Okay, so the structure of this is always similar. So here you will have now also the expected value of the energy. Okay, so these equations of motion have been derived by McLachlan. So let me also give you maybe just the name of the quantum chemist, actually, who derived these equations. And these are known as the McLachlan time-dependent variational principle. Okay? Again, these are equations of motion in the case where these theta dots, so my variational parameters, are real. Now, it should be, so the reason why I derived this equation of motion is because he wanted to do time-dependent Hartree-Fock, so essentially study what happens to chemical systems when you make your orbitals time-dependent. So this can be taken, for example, to be real, and he derived these equations. There is a special version of these equations, which was derived before by Dirac and Frenkel, that applies to the case in which we take these parameters to be complex. However, it's a more restricted version of these equations in which you are assuming that the variational state that you are working with is holomorphic, so which means that you can take complex gradients. So this is more general because I'm not assuming holomorphicity, but only differentiability with respect to these real parameters. Okay, good. So we are almost there because we have now an equation of motion for my variational parameters. I just need a way to estimate, if you want, these quantities, S and F stochastically, or if you want, using my favorite variational Monte Carlo approaches. And this is very easily done because we can rewrite, if you want, for example, a part at least of this metric tensor. So let's say this one, which is the most important. So if you want, I can insert a completeness now in between these two states. Okay, so I can rewrite this as psi x. So x, the derivative with respect to k prime psi. Okay. And now what I can do is that I can rewrite all of this with the usual trick that we use in variational Monte Carlo by multiplying and dividing by psi of x squared. Okay. So which means that I think that also Antoine showed this in the case of ground states, But essentially, if I now multiply by psi of x squared, and now I also divide by this, you see that I can rewrite this as divided by psi x, and then here I have the same quantity but with k prime. Okay? So you see that I managed to rewrite at least, okay, then there is another part of the tensor that I'm not writing down, these connected elements. But let's say the most important part already of this overlap can be written in most cases as the expected value over this probability distribution, which is the Born distribution of, if you want, the correlator, this correlator, which is the product between two the gradients of the log of the wave function, if you want, as you can read it from here. So I can rewrite this as the expected value over my probability distribution for my quantum numbers x. For example, this could be my spin projections or similar, of what we sometimes call dk star of x times dk prime of x. Okay? Where dk is defined, if you want, here. So this would be dk of x by definition. Great. So now we have a complete scheme, if you want, to estimate all the quantities. So similarly, you can also estimate this quantity f. I'm not going into the details, but it's very similar. So we have a scheme to estimate all the quantities that enter into these Maclachlan equations of motion. So then what we do is that at each time step, we update, if you want, our variational parameters in a way that their time derivatives follows this optimal equation. So which means that at each time step, we sample from our probability density psi of theta of t of x squared. So we sample x from this. We we estimate with Monte Carlo estimates these correlators, for example, and similarly for the f. Once we have stochastic estimates for both s and f, we invert these equations. So if you want, we solve for the unknowns theta dot, and then we have the time derivatives that are ready for the next step. Okay? And this scheme is known as time-dependent variational Monte Carlo. Yeah, so it's something that I did in collaboration with others at CISA during my PhD thesis. So it's a paper from 2009 or 10, I don't remember. I think it's, no, wait, okay, I don't know. I think it's 11, but I will need to check. In any case, so this is the main scheme that we'll use today. Combined, again, with our favorite variational ansatz, let's say a neural network quantum state to represent my psi of t. Okay? But the only thing that I want to attract your attention onto is that this kind of approach that we're using now to solve this, the initial problem, which was our Schrödinger equation, is different from standard applications of machine learning. In the sense that we don't have, if you want, a loss function, a global loss function that we are trying to minimize, as for example for the ground state, but rather our loss function is purely quadratic, so very easy to minimize. However, what we do is that we evolve in time our parameters. So in a sense, it's an easier problem, at least in theory, than optimizing for the ground state, because we are just evolving in time our variational parameters. We are not looking for a global minimum in this sense. Okay? So are there questions before I move to the slides? If not, I will give you now a short overview of the kind of applications that we can do. Yeah.
Trick, indeed, I also discussed in one of the first lectures.
Yeah.
What about configurations where psi vanishes?
I'll talk about those in a second. Okay, good. So let me go. So as a matter of principle, so all of this is very nice. It's very methodological, but we also want to apply, of course, these ideas to problems that have interest both in pure applications of statistical mechanics or quantum mechanics and other problems that are unsolved in the field. So one of the main applications I would say that these techniques have seen is in the context of auto-equilibrium problems. There are many other possibles, of course, because as soon as you have a time-dependent, if you want, Schrödinger equation, you can solve and study many problems, but I will focus on these out-of-equilibrium problems. So in general, there are many ways to drive a system out of equilibrium, and there are many questions associated with each of these fundamental or different protocols. So one of the most common, or if you want, mostly adopted protocols, both experimental and theoretically studied, is what we call quantum quenches. So essentially, we start with some pure state psi that we can prepare easily experimentally or theoretically, let's say mean field state. And then we apply the time evolution induced by some purely unitary time evolution induced by some strongly interacting, typically Hamiltonian. So this is what we call a quantum quench. And then, for example, one of the fundamental questions is that if you are in a closed system, so this is purely unitary dynamics, you might ask how can you reconcile this time evolution of a purely unitary time dynamics with Boltzmann, right? So the fact that you expect after some time that you are ergodic, and then the system has some intrinsic temperature given by the expected value, if you want, of the energy over this time-evolved state. So, for example, you can ask how fast equilibrium is reached. Is equilibrium reached? This is also a very important question. And what is the temperature that you thermalize to? So this is really a fundamental question in statistical mechanics, if you want. There are other ways, however, to drive Hamiltonians, to drive systems out of equilibrium. So one other way is introducing driving Hamiltonians, where in general now your h depends on time. So if we insist on writing this as an exponential of an Hamiltonian, you will need to take care of the time-ordered product, so in this way. And this kind of systems, or if you want, of driving Hamiltonians are related, for example, to what Antoine showed in the previous lecture, where he showed experiments with cold atom, ultra cold atoms, with Rydbergs, where you have some time dependence in your, for example, transverse fields, and these can be used to prepare a certain state. And indeed, one of the questions that you can ask in this case is if there is defect production when you cross a phase transition, so the mechanism of Kibble and Zurek, or if there are consequences for preparing a given ground state in what we call adiabatic state preparation. Now, if you look at the techniques that we have available, so the situation is not as developed, I would say, as for ground state methods, because solving dynamics, at least on a classical computer, is intrinsically challenging. So I will not go through all of this, but essentially, if you do exact approaches, you are limited, as you know, to small systems. If you try to do path integral Monte Carlo, you are severely limited to the fact that you have a severe phase problem, not even a sign problem, but a phase problem due to the fact that your wave function is not only non-positive, but it's even complex in this case. So you can't really interpret any of this as a probability density. And the other methods, for example, tensor networks, are typically limited to 1D systems in discrete space. And they are limited by entanglement. So, for example, if you want to use this for two-dimensional and volume-low systems, this is going to be very challenging. Mean field is very nice, but in most cases, I would say it gives a wrong both qualitative and quantitative description. Not always, but there are many known cases where even the qualitative features that you get from mean field dynamics are wrong. Whereas for ground state, this is not necessarily the case. Quantum computing is, of course, the other main contender in the arena because, as you know, that's the main reason why we want to build quantum computers, because they are able to do dynamics exactly. However, the problem is that they are strongly affected by experimental noise, decoherence, for example, which means, so this is my own assessment, so maybe not everybody shares this, but that if you want to tackle regimes that are truly hard for all these other methods and also these others, you will really need to have quantum error-corrected hardware, which is not going to happen in the next decade, I guess. So it's true that we still have a lot to do in computational physics, quantum physics, to solve this problem more accurately. So by introducing this kind of techniques, we can have a handle of maybe on other regimes that we are not accessible by the other approaches. So if we look at spin dynamics, which is one, again, prototypical example that is also related pretty much to what Antoine was saying, what we can do is that we can study, for example, a quench. Again, we start from a simple ground state, for example, of this transverse field now Ising-Hamiltonian, and then we, for example, we can prepare the system in the ground state for, let's say, h equal 4 or h equal 1 half, as in these two curves here. And then we can quench, so we can tune the final Hamiltonian to a certain value of the transverse field, which is equal to 1, which is the critical value, in this case, of the one-dimensional transverse field Ising model, or to 2, which is above the critical value. So this is some of the results that we obtained in the early paper, so where we used the restricted Boltzmann machines to describe the dynamics of this in this system. And you can see that you can see a qualitative feature emerging, so the fact that after some times local observables, so in this case the magnetization along the x direction, somehow thermalizes to a quantity. And you can see that with the very simple RBM, which is this orange line, we can describe to a good degree of accuracy what happens in this quantum system. So the same is true also for other cases that we studied, again, in this early work using RBMs. So for example, in the case of the anisotropic Heisenberg model, so here we have an anisotropy in the JZ, if you want, interaction, sigma z, that we tune from 1 to 2 when we do, for example, the quench. So after this, there has been a lot of work in trying to improve our approaches and to extend them also to more modern, if you want, architectures that go beyond these simple toy models, which are restricted Boltzmann machines. And in this paper, a very nice work that I'm quoting here. This should be Schmidt without an I. Sorry about this, this spelling mistake. So Markus Schmidt and Markus Heil already in 2020 extended, if you want, these variational states in a way to use convolutional neural networks. So convolutional neural networks are really suitable to describing now two-dimensional systems, which are the most challenging for all existing techniques and also for experiments, I would argue, if you want to study dynamics of strongly interacting quantum systems. So in this case, again, focusing on our favorite model, the transverse field Ising model, now in 2 dimensions, so for which we don't have any exact solution for the dynamics. So they did a similarly minded, if you want, construction where they do a quench starting from a fully polarized state in the x direction and quenching to some value of the transverse field, which in this case is twice the critical field and the critical field divided by 10. So what you can see in these curves are, for example, the observables. So here, this is again the value of sigma x as a function of time. This is done already on a system sites where you cannot do exact diagonalization. This is a 10 by 10 lattice, if I remember correctly, or similar. What they showed is that, for example, they can trace the dynamics for times that are typically longer than what you can access with other approaches, for example, based on tensor networks, such as IPEPs. So, for example, this is the IPEPs line, the blue one. And with this TVMC approach, based on neural networks, you can typically go to longer times. Typically, there are some other regimes where you stop a bit earlier. And the way to control, if you want, the error that you make in this scheme is to plot what I called here delta squared. So if you want this distance between the exact state and the approximate one, which is in this plot called instead r squared, but it's essentially the same quantity. And you can see that by increasing the depth of the network, which corresponds to these different color schemes. So the deeper networks are with these red colors. So you can see that r squared can be brought to smaller and smaller values by increasing the depth of the networks. And you can see that also observables tend to converge when you increase the depth of the network in this way. There have been also more recent applications of this idea to time-dependent Hamiltonians. I want to cite this very nice work again by the same group of people with the addition, notable addition of Zurek, so the same of the famous Kibble-Zurek mechanism. So in this paper that I just wanted to flash, and you can read it here, they studied again some violation actually of the simple Kibble-Zurek mechanism in 2 dimensions when they drive the system through a phase transition. So the same Hamiltonian again, but now they have a linear ramp, if you want, in the transverse field, in this case G of t. So they study some corrections also analytically, and they verify that this is exactly what you observe in numerical simulations. Okay, so far so good. So we've been describing some unitary dynamics induced by, for example, a Hamiltonian. The Hamiltonian we were interested in was mostly the transverse field Ising model. However, as you know, in general, unitary dynamics can be used, can be described, if you want, with another language which is completely equivalent, but used by another community, which is the language of quantum circuits. So a quantum circuit essentially is typically depicted in this way. For example, this is a circuit with 3 qubits that are initialized in the 0 register. Then I apply Hadamard the gate on each of them, and then some CNOTs. And as you know, for those of you who have taken courses in quantum computing, quantum information, you know that any quantum circuit can be decomposed into the product of elementary gates. Okay? So for example, this is a result due by Solev and Kitaev. You can decompose, again, an arbitrary circuit that is the product of local unitaries in terms of, for example, these 3 unitaries that I'm using in the following. These are not the only choices, but this is what I will be using in the following. So for example, you can use just RZ rotations. So these are, if you want, these kind of gates, diagonal gates, where you rotate, where you have e to the minus I z theta, where theta is some parameter. I have the Hadamard gate, not to be confused with the Hamiltonian. Unfortunately, they have the same symbol, which is, again, a single cubic gate that allows you, for example, to measure in the sigma x direction. And then you have control Z gates. These are truly entangling gates that act on 2 qubits, for example, this one and this one. Okay? So these are enough, for example, to describe an arbitrary quantum computation. So the question, if you want, is can we simulate arbitrary now quantum processes, unitary quantum processes described by gates, also with the help of neural networks? This is an extension of this scheme that was devised before neural networks, that is general and works for Hamiltonians, to the case of unitaries. And this is what we did in this paper. So the idea is that, for example, if you start with an RBM that describes the state of your quantum circuit at time, discrete time now, k, you can apply some 2 out of 3 of these universal gates exactly. So which means that, for example, if I have this RZ gate and I apply it on my quantum state, which is described by my neural network, I can get the output state after the application of this elementary gate exactly with just introducing some small modifications of the weights. So Antoine has showed you these figures, so these plots before, but essentially you can show that if I apply, for example, this RZ gate, the only thing that I have to do in order to describe the state after the gate is to slightly change these weights that are connected to the visible spin or visible qubit on which this RZ gate acts on. So this can be shown analytically, it's done here. The same thing can be proven also for arbitrarily entangling gates, for example, so arbitrary diagonal entangling gates such as the control Z. And you can show that, for example, they will just introduce an extra hidden unit that couples the 2 spins of the 2 qubits. So as you can see, then, I can describe exactly almost all gates that enter universal quantum algorithms. The only gate that I don't know how to do, and this is crucial, is the Hadamard gate. So if you want, the only problem, so the only obstruction that is between us simulating exactly all quantum computation is the Hadamard gate. So it's the only gate that we don't know how to do exactly on, for example, a neural network described by an RBM. So the main issue, this is the mathematical problem, if you want, that if I have the sum of 2 RBMs, so a superposition, if you want, of 2 RBMs that come out of this entangling gate, so this is superposition gate H, is not in general an RBM. So this is the mathematical problem. If I have the sum of two RBMs with different weights, this is not a third RBM with another set of weights. But in general, it is what we call a DBM, so a deep Boltzmann machine, where I have to introduce now a deep layer of connections that is written, that you can see written in here. However, the main problem with these DBMs is that if the number of deep neurons, so units that we have here, increases, so it's polynomial, so it's large, I don't know how to compute the amplitudes of this object analytically. Contrary instead to the case of the RBM, where you've seen the calculation done explicitly by Antoine. And you can show that if every time I apply a Hadamard gate, I increase by 1 the number of deep units, which means that after a certain number of Hadamards, the cost of evaluating this will be exponential, so I go back to the original problem. However, we don't care about this, because what we can do is that we can approximate the Hadamard as much as we've done here. So if you want, if I start now with my initial state psi and I apply the Hadamard, again, this is not the Hamiltonian, it's the Hadamard gate, what I can do is that I can try to find some set of theta primes, so variational parameters, such that they approximate as much as possible my state after the gate. And I can do that by minimizing something very similar to this, but to be more precise, I minimize the infidelity between my state theta prime and my target state phi. And this will be now a highly nonlinear function, so it's not a quadratic form as before, but it's now a nonlinear function of my parameters, changes, and as a function of theta primes. So we show that this can be also done with the usual tricks using statistical expected values. So for example, you can write this fidelity as the product of these ratios between the target state and the initial state. I will not go into the details, but if you want to have a look, please go to that paper. Now, this is important because it allows us also to connect to, if you want, variational error, what I call variational error versus hardware error. What do I mean by this? What I mean is that when we run our quantum circuit on our classical computer, so with our neural network, every time we encounter a Hadamard in our simulation, we have to pay a price that we don't know how to perform this gate exactly, but we have to try to maximize the fidelity or minimize the infidelity of this operation. However, this is reminiscent actually of what happens in a non-error corrected experiment, where every time you apply a gate, you cannot apply the gate exactly because you have imperfections, and the gate, for example, a Hadamard will be applied only with some finite fidelity of 99 or similar. So this means that to some extent we can compare the error that stems from our variational approximation to the error that stems from the, for example, depolarization noise or any other imperfection that you have on the quantum hardware, on the quantum computer. And the point that we made already in this paper, that was also later made in this other paper by Xavier Vental and others, where they used the matrix product states, is that you can compare the intrinsic noise error that you have in the experiment with this variational error. And if your quantum hardware has a noise level that is larger than the variational error, you are better off running your quantum algorithm with a classical simulator rather than with a quantum computer. So, for example, we show that with a simple RBM, running a quantum Fourier transform would need to be so for the hardware to be competitive, you would need a noise level of about 10 to the minus 3 per single Hadamard or per C0, for example, which is not so trivial to achieve with current experiments. So I will just flash maybe another application, which was to later on in simulating other more complicated circuits. For example, we simulated this circuit which is known as the QAOA. So essentially the circuit where you have this kind of, it's a trotterization of the transverse field Ising model, where you have these gates here that are just single qubit rotation of this form, with some parameter beta. And then you have these entangling gates that have this form that is instead diagonal in the computational basis. And as I was telling you before, we know how to do these gates that are diagonal in the computational basis exactly. But we have to approximate these entangling gates, these superposition gates, such as these rotations. So in this paper, for example, we did exactly this. So we approximated this and then performed exactly these entangling gates. So notice that we are in a reverse position with respect to the experiment, because for the experiment, it's much harder to do this with high fidelity, whereas we can do this with fidelity 1. And instead, for them, it's easier to do these single cubic gates with high fidelity, and in our case, it's harder. So we are in a somehow complementary spot. So we did some benchmarks, but what I want to show you is that we can manage to simulate, for example, 54 qubits, which is a decently large system size, for example, of the order of what Google can do in their quantum experiments. And here we can simulate this number of gates using essentially an office workstation for a couple of hours using an RBM, with a fidelity that we estimate is larger than the current experiments that you can run on these circuits using, for example, again, Google's hardware. And what you can see here are just different cost functions. So here at the end of the circuit, we measure the energy. For example, we measure this cost with the energy in the ZZ channel, if you want, as a function of some parameters. And you can see that when we go to p equal 4, you cannot compute this exactly. And we have if you want, a prediction that could be tested by the experiments if they run our same circuit. I just wanted to conclude this part by saying that one of the reasons this kind of approaches is interesting is because we are not limited typically by entanglement considerations, because, for example, the weights in your reciprocal machine can be taken to be arbitrarily long-ranged, which means that I can, for example, represent volume law states in a typically inefficient way. And for example, we did a small comparison to the same simulation run with Med-Explorer states, for example, on 54 qubits. And we showed that if you want to achieve the same accuracy, you will need a bond dimension which is essentially beyond of reach for current state-of-the-art Med-Explorer states. And this will become even more severe if we go to larger systems. So you see that going from 20, which is still doable by MPS, to 54, you have an exponential increase in this bond dimension. So I will start going to the conclusions. Maybe I'll take 5. Yeah.
Maybe Giuseppe, I have a question. So from the previous work that we just discussed, and also the papers reported by Fondamentale.
Yeah.
So one can deduce some level of noise below which the classical algorithm will eventually become worse.
Yeah.
Can you give us some?
Yeah. So this depends strongly on the quantum algorithm that you want to run. So, but let's say for a quantum simulation, I am personally interested in, which means doing Trotter dynamics of some interesting Hamiltonian. I would say that we can, this 10 to the minus 3 or below, actually, if you use deeper neural networks, is more or less a good ballpark estimate on the 2 cubic gates, I would say, for the case of the quantum algorithm.
When will the quantum machines lie?
Well, it depends, again, a lot, but for most, now I don't want to give random numbers, but I would say that, it's around here, maybe at the moment, maybe, yeah. So it's not so far, but we are also moving this line a bit below, so it's a kind of, it depends also on the architecture. For example, ions have typically better fidelities it depends. Okay, so the only thing that I wanted to say is that so in general, and this is one of the if you want, of the more general messages that you can take from this, is that if you have these quantum neural network quantum states, you can hope at least to describe some states that have large entanglement entropy, that are typically instead harder for approaches that are based on the idea that you want to compress the entanglement entropy, so, such as, for example, Med-Explorer states or PEPs in 2 dimensions. So what we showed in this paper is that indeed, if you restrict yourself to quantum states that have polynomially many parameters, which is the only ones we can work with in practice, you can prove, if you want analytically, that the neural quantum states can describe all Med-Explorer states of polynomial bond dimension, and in turn also all gapped 1D Hamiltonians, And all PEPs you can contract with a classical computer, essentially. So this means that there is really an interest in using these representations because they give you some extra space in this in this diagram compared to some other approaches that have other merits, but that might be limited to small entanglement. So the last thing that I wanted to tell you in the last 2 minutes is to answer actually Antoine's question, is one of the latest applications we've been doing, which is unit dynamics with measurements. So if you want something that I've not been considering in this framework and also in the previous one is what happens if I measure my system in between my one time step and the other, or in between one circuit step and the other. This is related actually to the question that Antoine was asking, that we've been investigating with Filippo and Vicentini and students at EPFL. And it's related to the fact that when I also cheated here, because I write this estimator of the quantum geometric tensor that you can see written here as this expected value of these correlators that now unfortunately I call O and not D, but okay, it's the same quantity than D here. So I was assuming somehow that the gradients of the state vanish if the state vanishes. So that's what Antoine was asking. So here I'm assuming when I divide by psi and multiply by psi that if psi is 0, this object also goes to 0. Otherwise, there is a problem. And indeed, the problem is that there is a bias term in addition to this Monte Carlo estimate of this S and F, so these forces and this geometric tensor. That in general is hard to estimate because this corresponds to state where psi is exactly 0 and D, so these derivatives, these O actually, are non-zero. So the solution, if you want to circumvent this problem, is to directly now minimize this quantity, or if you want the trotterized version of the unit dynamics, with respect to the theta tilde, so without passing, if you want, in this linearized problem, and writing down the infidelity in a way that I will not write down because it's a bit technical, that does not contain this issue of the zeros. So this is essentially what we are working out in this paper. You have to wait for the archive version to appear. But essentially, it's, again, the idea is very, very simple. It's based on the idea of minimizing the infidelity rather in its full version rather than in this linearized version that we have here. And this solves or circumvents greatly the problem of the zeros that can appear, for example, quite frequently if you have a measurement when you collapse your state into a product state. So one application was that we studied is, again, our favorite toy model, is TFI, where we now introduce measurements at each time step. So what we do is that we evolve the system with our time-dependent, with our Hamiltonian, interacting Hamiltonian, but once in a while, so at each time step here, we pick randomly some of the spins and we measure them, so as it is indicated here. So we for example, in this plot, what we would do is that we would have measured this spin to be up and these others to be down. Okay? So we have collapsed the wave function on these spins, but not on the others. So we do a partial measurement of the system with a random probability of measuring a given state. Okay? And we do this many times with some fixed probability of measuring the system. So this is a preliminary exploration of this two-dimensional system, which is very hard to access with any other technique, maybe only experimentally once we have better quantum computers. But what we find already in this case, these are again very preliminary results, so take them with a grain of salt, is that the entanglement entropy that you can measure in this case by doing bipartition, for example, of the system, would increase as a function of time. So this is for different system sizes. This is up to 6 by 6, but we can go a bit beyond this. Essentially, we find that there is, in this regime of small measurement rates, a violation of the area law of entanglement, which is compatible with the fact that we are measuring, if you want, the system not often enough with this rate. Instead, if we did measurements more often, we would find that the system would collapse to essentially a volume law, an area law state. So this is, again, very preliminary. We will put more precise results online soon. OK, so some final thoughts. So I just wanted to mention that for what concerns ground states, the use of neural network wave functions have seen really an explosion in the past few years. And starting from the very simple RBMs to the now much more complicated and complex wave function based on deep neural networks, we've seen applications ranging from many different domains. And one of the beautiful aspects that I found of this problem is that these wave functions are extremely versatile. So you can use essentially the same functional form to study systems at very different energy scales or even very different quantum states that do not share, if you want, the same degrees of freedom. So, for example, starting from electrons on a lattice, or just electronic degrees of freedom or spin degrees of freedom, we use, for example, recently some applications also with one-to-one of these wave functions for fermions. But then we moved also to study more chemical problems where you also have the nuclei, if you want. This is what I meant to draw here. And then finally, we actually also studied the nuclei only. So we zoomed in this other pretty much complicated many-body problem and solved for the wave function of the actual protons and neutrons that you have in the nuclei rather than the electrons only. So this by using essentially the same wave functions without too many modifications. And prototyping from one end to the other is really fast thanks to the flexibility of these neural network approaches. So this was for ground states, where I would claim that these quantum states based on neural networks are now the state-of-the-art essentially in all quantum problems, especially in 2 dimensions and in continuous space. In 1D, there is, of course, matrix product states that are competitive and actually extremely efficient in solving 1D problems, but in 2 dimensions and in continuous space, I would claim that these are now the new state-of-the-art for ground state wave functions. Now, the problem, one of the most challenging problems is studying dynamics. So that's why I also told you about this, because we need also, if you want, new ideas and new improvements over what we can do right now. We are limited to much smaller systems, as you've seen, than ground states. And its present formulation, the variational dynamics, is much harder, heavier, if you want, problem than the ground state search, because we have to do this. Even though we don't have a global optimization problem, we have to evolve our state in time, and this can take, for example, small time steps, and inverting this system can be challenging. So there's been great progress in the field, but we are still not yet at the point where we have general purpose, if you want, quantum simulators that can simulate with sufficient accuracy any physically interesting quantum system. So we have to work to go there. And I also believe that we can try at least to combine some of the power of quantum computers with some of the ideas that we've been developing in the context of classical machine learning. So this is one of the frontiers that we are, for example, exploring, and where there can be interplay between these 2 fields. And also, what you cannot expect in the near future is having an assistant that magically solves problems for you with this artificial intelligence or these machine learning techniques. We are not there yet, and I think we will not be there yet in the foreseeable years, at least. So, for example, if you try to ask ChatGPT to solve for the dynamics of the transverse field dicing model in 2 dimensions for a very specific set of parameters, he writes the correct equations. He knows about some of these things. He writes also the Hamiltonian, and it also tells you that you have to use the time-dependent variational principle, which is exactly what I was presenting to you this morning. I didn't trick it into this answer, but as you can say, it cannot really solve the problem for you. We are not there at the point where we can interface, if you want, this kind of approaches to these other, much more computationally heavy methods, where we have to rely, and then we have to polish, if you want, our metals and feed them to the machine. So there's this still, if you want, dystopian part of the story, where we have to really work hard on making our problems suitable for the machine. All this magic is not happening yet, but that's where we need more, energy, and where we need more ideas from young researchers, especially. Well, not that the old ones are not welcome, but since I see many young people in the audience, to have new, if you want, intuition on how to solve these problems. So thank you, and I leave the room open for questions. Yeah, thank you.